Mesdames et messieurs, bonsoir.
Ladies and gentlemen, good evening. Welcome to the fifth presentation of the 19th Right Colloquium in the conditions you are familiar with. Online, no one in this huge hall, 600 participants could have been here, but that's not the case tonight. If you missed the 4 presentations of the week, you can find them on the Right Colloquium website. My name is Olivier Desibourg. I am a scientific journalist, and I am going to again have the pleasure and honor of emceeing this evening. As you know, every colloquium we welcome scientists of worldwide reputation. Again, this week we were able to travel with these experts in the wonderful world of mathematics, perhaps not the same mathematicians you met at school. So we talked about butterfly wings flapping with Gis and the law of thermodynamics with Laura Saint-Raymond. On Wednesday, we traveled between the galaxies and the atoms and the dimensions of physics with Martin Hera. Yesterday, we talked about music with Alain Cohn, and this evening, we are going to discover something different with Professor Smirnov. But this brings to mind a quotation of Henri Poincaré. Mathematics is the art of giving different names to same things. So we're going to listen to our speaker for about 45 minutes, and then we'll have a Q&A session online. You can put your questions. There's a small white square on the Right Colloquium website. If you're on YouTube or Facebook, switch back to the Right Colloquium website and put your question. Don't forget to do it during the presentation, because we'll have somebody on stage that will put the questions to our speaker for this evening. We are going to introduce the speaker later on, but for the last time, I'd like to give the floor to the president of the Right Foundation, Thierry Courvoisier, and he's going to say a few words of introduction. You have the floor, sir.
Merci, Olivier.
Thank you, Olivier. Ladies and gentlemen, good evening. Welcome to the fifth and last evening of this year's colloquium. You're still at home. I hope you're enjoying a drink and you're well set up for this evening, and you're going to be able to learn more about the mathematics, which is the theme of this year's Right Colloquium series of conferences. So we've seen and heard mathematics in a dialogue with physics, meteorology, small and large scales, music, forms, and literature. I think time has come to discuss the very nature of mathematics. Are they reality, fruit of our imagination, a reflection of the physical world, tool? All of that, something else. I'm very grateful to Stanislav Smirnov for having accepted to rise to the challenge to end this week. Stanislav doesn't replace Vaughan Jones, who was supposed to speak this evening. He's going to give us an original viewpoint coming from his in-depth knowledge of mathematics. And then we are also going to listen to what Anton Alexeyev will say about Vaughan Jones, and I'm very grateful to him to create and establish this link with the speaker who's won't be able to be with us this evening. This being said, I wish you an excellent evening, and I'll come back to say a few words at the end of the discussion. Thank you, Thierry Courvoisier. We talked about interactivity, and you can put your questions in French and English, and you can also listen to the presentation in English. You have a small icon at the bottom of your screen which you need to click on if you want to listen to the presentation in English, so you can put questions in English, and naturally during the discussion that will take place after the presentation. So I'm now going to give the floor to Anton Alexeyev, who's a professor of mathematics at the University of Geneva, who is behind the whole organization of the colloquium this year. Ladies and gentlemen, members in the audience, today I would like to start off by paying tribute to Vaughan Jones. He came to us from New Zealand. He came to Geneva to write up his thesis in physics, and then he changed his mind and decided to write a thesis in mathematics with as an advisor the great mathematician from Geneva, André Hefliger, who was in fact a worldwide known surveyor, but Jones decided to go for an algebraic structure in an analytical context. And after his dissertation, pursuing his work, he made a tremendous discovery, which is now called the Jones polynomials. So I'd like to show you a few pictures of this polynomials. This is the knot theory, knots that you're familiar with, sailors' knots or mountain climbers or knots that we use. You see two knots here, and Jones associates with these knots polynomials, which we now call Jones polynomials. You see the knots are different and the polynomials are different. So it's a fantastic discovery because it establishes a link between this classical subject, i.e. knots, and quantum physics. So it's totally unexpected, and now we have a whole area in mathematics which we call quantum topology, which is born of this discovery by Jones. This is one of the founding articles written by a well-known physicist, Vittel. As you can see, there are more than 5,000 citations, which is enormous in our field. So apart from these major scientific discoveries, I mean, Vaughan Jones was a very warm person, full of compassion for other people. We miss him terribly. I should have taken the floor this evening, and we're missing him this evening, and we're going to miss him in the years to come. Allow me now to introduce the speaker for this evening, Professor Stanislav Smirnov from the University of Geneva. Stanislav wrote up his dissertation at Caltech. He taught as a professor in Stockholm before coming to Geneva in 2003. He discovered important things that link analysis, combinatory and mathematical physics. And here you can see on the screen the percolation model that was solved by Stanislav with this blue path. You see this red path, in fact, which meanders in the drawing. So he was awarded all sorts of prizes, in particular the Fields Medal in 2010. And this evening he's going to talk to us about mathematics, art or science. So I wish you a very pleasant evening indeed with Stanislav Smirnov.
Alors, je peux commencer?
Well, can I start?
Est-ce que je peux déjà commencer?
Can I start? Yes, yes. Please do so. Thank you very much indeed, and thanks to Anton for this presentation, and my greetings and thanks to the Wright Foundation for inviting me to this very interesting symposium. It's with great pleasure that I share some ideas with you, even though I'm very sad to do that instead of my great friend Vaughan Jones. It's very difficult to be the last one to intervene in such a colloquium, because many things have already been said. There is something quite striking coming out from the three previous presentations. There are many explanations for mathematics, scientific ones and philosophical ones and others. The three motivations to study mathematics exist or have been in existence for many, many thousand years. Where do mathematics come from? How do scientists choose problems to solve? Let's start with history. Over 4,000 years ago, human beings started to observe interesting regularities in the natural world, in arithmetics and in geometry. The role of mathematics is to explain things, and I'd like to mention three ancient objects which impressed me very much when I saw them in museums. The first one is a papyrus, a scroll which can be seen in the Pushkin Museum in Moscow. It's one of the oldest mathematical objects, dating back to 1,850 years before Christ. It's a very long scroll, 7 meters long, which was deciphered a couple of years ago. And you can find on this papyrus about 30 different problems, such like this one. In this class, you can see, for example, a problem with a kind of drawing. The problem being finding the volume of the trunk of a pyramid. Other problems have been mentioned in this papyrus with their solutions. You can imagine that the problem of the volume of a pyramid was extremely important for ancient Egyptians, so it is mentioned in many occasions. So that can be explained. But you can also find these problems in exams in secondary schools nowadays, so things haven't changed that much. But I also would like to mention another more mysterious object. This is a tablet in ceramics from Babylon, about as old as the Egyptian scroll, which you can see at Yale University in New Haven. And what you can see here, cuneiform writing, not with words, but with numbers. Even if you don't speak Babylonian, you can decipher these figures. You see these figures representing digits, so you can read here 1, 2, 4, etc., etc. But you have to be careful, because it is not 2 and 4, but it's 2 vertically, which means 20, and then 4. So indeed, you can find 4 different numbers found here, 1, 24, 51, and 10. But what you have to know is that this hexadecimal system had been in use in Babylon. But it's difficult to use 60 different figures, so they used only 10 figures. If I calculate this number according to that system, you have to write 1 times 60 to the third, and plus 24 times 60 squared, plus 51 times 60 plus 10. It's difficult to understand because Babylonians did not use a comma or decimal point. So you should have a decimal point here between 1 and 24. As a matter of fact, it is a fraction. It's 1 plus 24 over 60 plus 51 over 60 squared, etc., etc. And you reach a number which is 1.41421296. And I'm sure that many people here or in front of their screens have already seen this number, because it's an approximation of the square root of 2. What's very interesting is that's a very good approximation. So it's quite clear that this is not something that you come at or arrive at for practical reasons. Obviously, practical use was not the motivation of the mathematician of the Babylonian times, all the more so since he was using a tablet. So it's not something that you just simply jot down. If you want to calculate a figure with that kind of precision, you have to think about it. So Babylonians 4,000 years ago, before our time, calculated with that kind of precision the square root of 2. But we don't know exactly why or which reason for. I forgot to say something. There are other numbers here. So after the square root of 2, that mathematician calculated the length of the square with a length of 30, which is the same thing as half in a decimal system. So I suppose this is only a draft of something, but there are many other tablets in museums in the world. And 2 years ago, a very interesting exhibition took place at the British Museum, because Sardanapalus, the king, Babylonian king, had a very rich library of 30,000 tablets. He was very proud of knowing mathematics, because in one of these tablets he wrote, "I, the king, I am able to solve divisions and mathematical multiplications which have no easy solution." So the third example I wanted to give you is another tablet from Babylon, which has many things written on it. It is to be seen in New York at Columbia University. What can we find here? The second line has a few numbers, and obviously the last column is just a series of lines, 1, 2, 3, 4, etc. But here you find 159 and 249 written in that way. So according to the hexadecimal system, it means 119 and 169. What is the meaning of these figures? I don't think that you can figure it out simply by seeing these two figures. But there are many other figures here. So obviously you have to take the square of 119. And if you add something to it, you will reach 169 squared. There is on this tablet a list of Pythagorean triples. In other words, ancient numbers such as a squared plus b squared equals c squared. It's quite probable that Babylonians knew already these rules quite a few centuries before Pythagoras. So they listed here 15 of these triplets. There are many conjectures, we don't know it for sure, but if you know the smallest one, the Pythagorean triangle with sides of 3, 4, and 5, you can already easily construct an angle of 90 degrees, which is important in land surveying. With other numbers, or you can, for example, create here the arcsinus of 5 over 13, etc., etc. On this tablet, you see the sinus of angles of Pythagorean triplets. So it may be a kind of trigonometry. Whatever, obviously this had been motivated by scientific interest and not by practical interest. It seems, therefore, that you have this Pythagorean theorem, but it's obvious that it was noticed to start with triangles having sides of 3, 4, and 5. At the time, the ancient Greek found out other Pythagorean triplets, but they wondered whether the equation a squared plus b squared equals c squared couldn't go to the equation x to the 4 plus y to the 4 is equal to z to the 4. In the 17th century, Fermat proved that there was no natural solution for that equation. But 200 years later, 25 years ago, an English mathematician, Andrew Wise, proved that there are no solutions for x to the n for all powers superior to 2. But if you use other powers, we don't know if there are mutually simple solutions. $1 million has been awarded or will be awarded to the one who can solve that problem. So what's interesting in that kind of problem is you take a Pythagorean theorem, which is something geometric, and then you start wondering about solutions for similar equations. And this led to a huge mathematical theory, the theory of numbers, where you can find many things and discover many other things. So you can say that mathematics are beautiful. My colleagues drew up a list of all the reasons why mathematics can be considered to be beautiful, because you can find a short explanation to a difficult formula, or you can have a complex theory which is elegant, or you have an unexpected connection. But the Pythagorean theorem is something both beautiful and very profound. It says that x squared plus y squared equals r squared, which is the radius of a circle. And that, as Henri Poincaré already, he was quoted already, he said, math is the art of giving the same name to different things. Well, the geometrical object, a circle, is expressed through an equation. And many other things can be done with the same numbers. But what's interesting in mathematics is that there is nearly always an influence on geometry and a connection between geometry and algebra. Hermann Weyl, a German mathematician, said that nowadays the angel of geometric intuition and the devil of algebraic abstraction are becoming the soul of every mathematician. So there is always a kind of connection between algebra and geometry. Let me say another word about this theorem of Pythagoras. There are many possible demonstrations. You have the proof by Euclid, which you can find in his handbook of geometry, but there is another kind of proof which has been attributed to Leonardo da Vinci. And nowadays there are very important generalizations of this theorem. For example, the Parseval theorem, where the demonstration is algebraic without using geometry at all. So what is the beauty of mathematics? Well, yesterday we heard the music of prime numbers. Here you see a formula, I plus e to the power I pi equals 0. It might be the most beautiful formula for mathematics. And on the right-hand side you see a sonata by Beethoven. But to be able to understand the beauty of these two objects, you have to have a certain kind of education. You can study this formula, but if you have no knowledge of mathematics, you won't feel its beauty. Same thing for the music here. However, you can listen to music, but with the exception of yesterday's presentation, mathematics can't be heard. There are quite a few mathematical objects which can be represented in a very interesting way. For example, objects which grow, like the Julia set, or you have limited aggregation by diffusion, which is something very important for physics. And here, without any knowledge of mathematics, you understand or you see that something is very interesting. The other thing that was discussed was the repercussions of mathematics. And I'd like just to give you the example of astronomy and how applications can enrich mathematics. Tycho Brahe made very precise observations of the movement of planets. Before him, people thought that the movement of planets were circles, but that is not the case. There are ellipses. And Johannes Kepler, who was an assistant of Brahe, analyzed his data and observed three empirical laws. The fact the areas, equal areas are scanned by the radii in equal times. So there was a mathematical question there. You have three geometrical lines. How can we explain them? And that was more or less explained by Newton. He developed a new area for mathematics, analysis. In order to explain these three laws, he developed this new area. We always, human beings always looked at the movement of planets, but before Newton there was no way of describing them in an abstract way. And thanks to him, analysis was created, and since then many new and further interesting questions were raised. So I think this is a very typical example of it's possible to make a very important input and create new developments. Eugene Wigner mentioned the unreasonable efficiency of mathematics in science and nature. And he began writing this essay by an anecdote of a statistician showing his friend his work on the evolution of populations, and the friend asked, what's that symbol here? And he said, well, that's pi. And what's pi? Well, it's the circumference of a circle of a diameter 1. And the friend says, now you're pulling my leg. Don't want me to believe that population has anything to do with the circumference of a circle. Well, it has indeed. The evolution of this formula is Gauss's equation. And as you can see here, I took a graph of marks given at an exam in the United States, and you can find exactly the same distribution. It's only statistics. It has nothing to do with geometry. So it's very interesting in mathematics. There are always links between different topics, but also with other types of science. So I highly recommend you to read this essay by Eugene Wigner. Now, I've come to the end of my historical discussion. I'd like to mention the heart of my presentation. In other words, how do mathematicians do to choose the problems that they're going to study in 2020? What's happening in mathematics nowadays? And the answer is there are many things going on right now. There are still many open questions. But what's interesting is that we still have many things to solve. Because, first of all, there is a constant flux and inflow of new problems, practical problems and other scientific problems. And every time we develop a new thing, new questions arise. In a few weeks, I'm supposed to discuss some of these problems in the conference. So I'd like to give you two examples drawn from my own experience. I think I can give, therefore, you a glimpse into the life of a mathematician. Let me start, as was already mentioned, with a mathematical question. How many curves can you draw on a grid? A grid of squares or of hexagons? You can draw this or that. There are, of course, many, many possibilities of drawing. But it's a pure mathematical question. But there is a very strong connection with physics. In Martin Herer's presentation, we already heard about this question in liaison with the Brownian movement. On the left-hand side, you see the Brownian. On the right-hand side, you see the Brownian movement of pollen particles. They move around because the small particles have this erratic Brownian movement. On the left-hand side, you see a random walk in 2 dimensions. Every second you go north, west, or south, etc., etc. And in the end, you obtain a kind of fractal drawing. What is the mathematical function that can explain or express all this? Then you can discuss, for example, a random walk in 3 dimensions, or plot the graph in 1 dimension. And you can already see that it's very close to what you can see on a stock exchange market. What kind of questions can one ask? First of all, how many possible curves can there be? It's a very easy question, because if I take a curve of a t length, every time I can go in 4 different directions, so the answer is 4 choices times 4 times 4 times 4, so it's 4 to the power t. And on a hexagonal grid, the answer is 3 to the power t. That was easy, but I can ask another question: where will we be in time t? We expect to be at distance t, but not here. The coordinates xt at time t is the sum of t steps plus or minus 1. In each mathematical presentation, you need a demonstration. This is mine here. It has already been mentioned by Martin Herer. Let's try and calculate the average value of xt squared. So the average of xt squared is the average of all these sums. An average in mathematics is described with the word E, like mathematical espérance. You have to develop the square of a sum, and you have expressions like Sj squared or Sij. And this second sum is null, because here you have the product of plus or minus 1 times plus or minus 1. There are 4 different possibilities. Plus and plus, plus and minus, minus and plus, minus and minus. And you reach 0 in each case. The first expression is the sum of squares of plus or minus 1, which is always 1. So it's a sum of 1, which equals t. Therefore, on average, xt squared equals t. And the average of xt is more or less equal to the square root of t. In t minus, you reach the existence of the square root of t, which is funny and important at the same time, because it is the reason why it is very difficult to predict the propagation of heat. Now, Let me turn to another question which has not yet been solved. So the question I mentioned earlier on was solved by mathematicians Albert Einstein and Norbert Wiener. But another question would be, if the trajectory is simple or self-avoiding, if there is, for example, the interdiction, the prohibition of going at the same point twice. This is a much more difficult question, because here you can go in 4 different directions, but now here you can only go in 3 directions. Here you can go in 3 directions. Here, but afterwards there is no possibility of going anywhere without being self-avoiding. So you have to be very careful, and it's very difficult to calculate the number of trajectories. If you want a small exercise, well, I can give you even 2 exercises to show that on the grid of 2 to the power t is smaller than c of t and smaller of 3 to the power t, and another exercise with the square root of 2 to the power t. The most difficult issue or question is it's difficult to show or demonstrate that c of t is more or less equal to mu to the power t. Mu is depending, therefore, on the grid. What is the value of mu, of course? But the other question is, if I take an average distance, which power of t is it going to be? This is a question that has been raised by mathematicians, but very surprisingly, a chemist asked the same question. Paul Flory, a Nobel laureate in chemistry, understood that for a linear molecule, like for example DNA on this photo, the composition of the molecule was important, but also its position in space. So he proposed to model the position of a linear molecule by self-avoiding walk or progression. In his book, he thought that on average the absolute value of xt was t to the power 3/4. He made a demonstration like a very elegant physicist, but unfortunately it wasn't very rigorous, and even after he received the Nobel Prize, people noticed afterwards that his demonstration was not quite correct. Self-avoiding progression goes farther than random progression, because self-avoiding progression has to go further. 30 years later, another scientist, a Dutch scientist, a physicist, Bernard Nijenhuis, improved on the formulation and also found out a value of mu for the hexagonal grid. Mu is the square root of 2 plus square root of 2. It's very unclear to know how such a number can find itself in a mathematical demonstration. And then he also said that there was an approximation for the number t. So he improved it to t to the power 11 over 30t. Mu depends on the grid, but this power does not. So you have this number 11 over 30t. It's very difficult to explain it. It's very rare that you have such a kind of fraction in mathematics. But in any case, all the formulations on this slide are derivatives, but in mathematical terms it's not very clear what you can do with it.
So what we tried to do with my colleague Duminil in Geneva is to show, starting with the hexagonal grid, we were able to show that mu equals the square root of 2 plus square root of 2. So if you calculate the number of trajectories of length t, we find that mu is equal to this value. So how did we show this? We started off with a very standard test that you study at home, so as to be able to come up with a series epsilon MAE of 0 to the power of x minus the length converges from x to mu and diverges from x if x is inferior to mu. And it's easy to show this because then you have a geometric series. So if x is greater than mu, there's convergence, and if x is smaller than mu, there is divergence. This is something that is done at school. So we look at this series. And so you have here 0 minus the length of the walk. So you here have the length and the walk. So as to be able to study this sum, we have f function of z equals epsilon MAE from 0 at z x to the power of x minus length. So we decided to add something, and we added an exponential where we have a number of turns. For instance, in this walk where you turn left and then right and then left, left, left. So the total is 4 times left, once right. So you have the numbers 1 minus 1 plus 1 plus 1 plus 1 equals 3. And if you don't want to use complex numbers, you can use these simple numbers, but obviously it works better with whole numbers. So with this sum, we see that it satisfies the law of knots of Kirchhoff. If alpha equals pi over 8x equals square root of 2 plus square root of 2. So this is something that you learn at school. So for f function of z, it tends towards 0. So it's relatively easy to check. So there are tricks where you can prove this. But then we come to the local law of knots. And from what we've learned at school in physics, we can infer global identities on f, and then infer the convergent divergence and the value of mu. And what's interesting, it's not easy to get there, but you can explain this to school children. And so you have mathematical analysis and physical intuition. So we started off with something in chemistry, then we added physics, and we came to this formula. I'd like to come back to the previous slide, because pi over 8 explains where we get to the square root of 2 plus square root of 2 equals x. So it's twice the signs of alpha. So twice the signs of alpha is this number here. So it's, and I refer you back to Bernard Nihus, who came up with this prediction. He said in another article, he explained this further. But as I said, when you show something, when you prove something, you create other problems. So you have here the law of knots. And if we can demonstrate the law of meshes, P plus Q plus R equals 0, as with the law of knots, A plus B plus C equals 0. So that was the first story. And what I think is very interesting is that this is question of physics and chemistry and mathematics, so it all comes together. And the second story I'd like to tell you is a question of biology, which was put by my Geneva colleague, the biologist Michel Milinkovic. He showed me these two pictures and he said, are these two pictures the same? Are they similar? So on the left-hand side, you've already seen this a grid. There's a random coloring. So as I say, it's random. And on the right-hand side, we have the skin of an ocellated lizard. So it's not this lizard here, because this is a chameleon, which is far more friendly than the lizard. But it's an interesting story. So we're here going to talk about the lizard. And here, something relatively interesting. It's not really random, because there seems to be connections here and there. So Michel, I mean, he's already conducted 2 years of experiments and has looked at the way in which the scales of the lizard skin change color. So you start off with black and then switch to green, and then periodically they change back again. So I was rather surprised when I found out this, because he came up with a conjecture that this was a cellular automaton. So this is a concept that was developed by von Neumann, John von Neumann, well known in the 20th century. He worked in the field of artificial intelligence and computers, and he wanted to come up with a model with very simple rules. You can build very complicated things. So he started off with a square grid with 19 different states, but then John Conway, the other mathematician from Princeton, who also passed away unfortunately this year, he played the game of life, which is just as complicated as a computer. The game is relatively simple. So the squares are either white or black. So if the cell is black, it means it's living. The dead cells with living neighbors, so here you have 3 living neighbors, then the cell is going to become alive again. So here you have 2 neighbors that are alive, then it's going to remain alive. But you could either die of overpopulation or of loneliness, solitude. But there's very interesting behavior that comes up. So here you have a stable population, nothing changes because every live square has a couple of live neighbors. But here, the cells at the center, you always have 2 live cells, but this one is either live with 1 neighbor or dead with these dead cells. But you can have other phenomena, 3 here and 3 there. But was even more interesting, after a couple of years of this game of life, somebody came up with moving pictures. So for instance, here or there, and you can come up with very complicated things where you see everything is happening at the same time, interactions. And the conclusion is that the game of life is just as complicated as Turing's machine or a computer or the universe. So you can model your laptop using the game of life. So you need a relatively big grid to do that, several hundred kilometers. And for the universe, you need a humongous grid. So this is a very interesting example which explains how you can get to very complicated things. But does this mean there is a link with what we are about? And I read this when I was much younger, and you can have more or less the same example that comes up in the in shells. You see these two shells here. So what happens here, you see the graph of the shells, which are built line by line. So you're not going to see this automaton at a given point, but from 0 to the end, i.e. the age of the shell. But I put the question to Michel, and he said that he wasn't able to answer that, but he had enough results from experiments he conducted that a lizard could be simulated by a cellular automaton. And so the question was how to explain this. But in terms of mathematics, you have to come up with a mathematical question. So we used a mathematical model, and it has already been done in the past. Alan Turing, who's well known because he solved the Enigma code during the Second World War. So he came up with a theory of morphogenesis. And you can understand where you get these graphics on animals' skins. So it's the same equation as the one we use in the random walk, but if you have a non-linear and reaction between the different colors, you can come up with interesting motifs. So here you see the results of the experiments that he conducted himself without a computer or on a piece of paper, so all sorts of equations. This equation came up with this drawing on the left, which looks a bit like the skin of a cow, or a Frisian cow at least. And if you use Turing's equation, you can come up with different motifs which are more chaotic. So everything that we see, for instance, in the world that surrounds us. So the question that we now need to answer is how can we link the lizards to this equation? And Michel obviously had conducted a number of experiments and worked on equations, and this is explains how we have these difficult motifs, because there are other reactions, an activator, an inhibitor, so that come into the whole equation. And this is something that was already known, and we could conduct experiments. But the problem is that what we see here for this lizard here is that every scale is a single color, either black or green. But for others, for most lizards, the motif has nothing to do with the color of the scales. So how do we get from here to there using Turing's equation? So we're back to mathematics yet again. So the conjecture is that between the scales of the lizard, the skin is finer between the scales. So we were able to show that in that case the diffusion coefficient is smaller. So if we have alpha, which is smaller in between the hexagons, so we can use the Turing's equation on the lizard skin, and we can use this reaction diffusion equation discretely on the network of scales, and this brings us to the cellular automaton of von Neumann. And that's what's so interesting, because we managed to carry out this calculation alpha h, which is a discrete model, and you see the rest of the equation at 30 degrees. But when we started the experiment, we found this result. So square root of 3, and this also applies to this lizard skin. But in terms of a cellular automaton, this is something that we'd all understood at a time, but this is an ongoing work using mathematics and physics, and we can use another model, that of Michael Fisher, for the Ising model, the two-dimensional critical Ising model. So this is what I think is really interesting. You start off with a biological question, then you get a bit of physics and chemistry and the mathematics, which are then used to link Turing's equation to Turing's equation, which is discrete. And how is this going to bring us to the cellular automaton? And this is yet to be solved, and I hope that we'll be able to solve this with Michel, my colleague, within a year. So this is the result of my personal work in mathematics, but obviously there are other things that can be done, obviously not necessarily in Athens, at the School of Mathematics in Athens, but I'm rather interested in the remaining pictures. Thank you. Thank you very much, Stanislav Smirnov, for this fascinating presentation. Now we're going to have a few minutes together, and we'll have discussions with you, and we have with us Anton Alexeyev and Elise Raphael from the Department of Mathematics at the University of Geneva, who is going to relay your questions. There are lots and lots of questions, and we're going to dwell on all these questions because it's the last evening. So while we wait for the first question, Stanislav, you know that we've seen this throughout the ages, the fascination we have for mathematics and the beauty of mathematics and the discovery of recurring structures, square root of 2, the golden number. Is it because you're looking for beauty somewhere along the way more than usefulness? And what is beauty all about in mathematics? What's the definition of beauty in mathematics? Well, the short answer, yes, of course I'm looking for beauty. But as I've already said, this is very subjective. I mean, it's like in art. You can appreciate an artist like Picasso if you already have a notion of art, and the same applies to mathematics. You need to be able to do maths so as to be able to understand the beauty of mathematics, and if there's a phenomenon which cannot be explained, and suddenly we come up with a solution, I find that extraordinary and I find that beautiful as far as I'm concerned. Well, it's a matter of elegance, of subjects perhaps where I didn't see obvious link, but perhaps even for old problems we're looking for new demonstrations that are either more elegant or shorter or use ideas which hadn't been used in the past. So that also explains the beauty of mathematics. And perhaps we're striving for the absolute truth. Mathematics are beautiful because they are true, or they are truer, or they are true forever and ever. Is that correct? Stanislav? Yes. I mean, it's different in physics, for instance, because we can conduct experiments in physics and this could change theories. But in mathematics, if it's been demonstrated once, that's it. It's been demonstrated for once, forever and ever. But for me, mathematics is a very pure science. So the first question on cellular automata. So how can you study them mathematically? Are there convergence criteria? Well, it's a rather complicated question. There are lots of books that have been written on cellular automata. The same applies to Turing. Lots of books have been written. But they're more numerical in nature than demonstrative, and there's a system of mathematical calculation where we can solve these problems. And Stephen Cram has published a major work on cellular automata. And so, an example. The cellular automata of shells is the most simple cellular automaton. But even for that automaton, there are a number of questions which are still put. And I'm going to share my screen with you. If I look at this cellular automaton of shells, you see here that there's a chaotic part here, and then there's an ordered part. It's not shown. This hasn't been proven. So if you want to study the theory of cellular automata, well, you've got a lot of work in front of you because there are lots of questions which have to be solved. We talked about the link between biology and mathematics and the motifs on the backs of lizards, and we've been heard a lot about the inefficacy of mathematics in biology. Well, it's a matter of logic. Wegener is a matter of logic. But I started off with this example of Newton. We couldn't discover the laws of Newton 2,000 years ago because we weren't able to make precise observations. As soon as that was possible, then arrived Newton on the scene, but nevertheless it remains an equation because until recently it was very difficult to do proper observations. So we thought perhaps it's more complicated than physics. But 25 years ago, there was this prize awarded $1 million so as to explain the genome, and today you can do the same thing for about $200. So we can solve a number of problems thanks to mathematics, and this is what we've done with Michel. It's relatively complicated, perhaps 30 years ago, to do the same thing. But today we can come up with observations that lead to more interesting questions. And I'm sure a lot will happen in the next 10 years. I have a similar question. Preparing for this evening, I came across an article of the CNRS. There are lots of mathematicians in France. So in the 80s, this was the physicist you mentioned earlier on who was awarded for the first time a Fields Medal, so to a non-mathematician. And in this article, this is it said that this is an increasing trend with physicists and laureates of Fields Medal that are working on problems that have links with physics, and this is something that you've confirmed. Do you agree with this trend? How can you explain that this is happening? Is this something to justify the very existence of mathematics as one tries to prove the sort of practical link in the physical world? Well, as I said, you can study mathematics. I mean, there's enough food for thought and enough problems to keep you busy a lifetime. And lots of friends who don't want to mix up physics and mathematics and prefer pure mathematics, although there are links sometimes between the two subjects. I've naturally read physics and mathematics, for instance, dynamics and analytical systems. So, I mean, it is quite normal. So I think one should try and strike a balance between the two. Some prefer physics, others prefer mathematics. So I think it's better to think in terms of synergy rather than try and find differences. Talked about interesting problems in mathematics, and somebody has asked us for mathematical objects. Can you create some mathematical objects and that you can create and that are not interesting? So how do you distinguish between interesting and non-interesting mathematical objects? Well, listen, some people prefer to eat ham and others prefer to eat watermelons. I mean, you know, it's a matter of choice, a matter of taste. And some prefer to do algebra, or others more interested in genetics. So it's up to you to carve your own path. And some topics perhaps are more fashionable, more with it, more sexy. In science, the same thing. But it's more a personal matter, personal choice. And we may have differences of opinion. That's fine. Different points of view. Listen, I don't have any experience when it comes to writing, but I've been told that when people write novels or books, the characters take on a life of their own. So the writer, in fact, cannot really change the character or decide which way that character is going to go. And I think this is the same. It applies also to mathematical objects. Sometimes we have a good object and it's going to impose its own role in the subject. And mathematicians that have created this object no longer have total control. So the mathematical object is going to develop on its own. So objects that have their own life are good objects. They develop and they go their own way. And mathematicians can continue to work with them, but they have this property of, they have a personality. So a comment from Michel Vinkovich, Good evening. I think beauty is a combination of complexity, non-linearity, and diversity, which is down to chance. I entirely agree, Michel. You're perfectly right. That's the advantage of online conferences. We can talk to everyone. There was another question which is far more global with the development of artificial intelligence or big data. What about ethical matters? Do we also need to talk about ethics when we discuss mathematics? Well, it's the same applies to all scientific fields. The atomic bomb, I mean, it's like a Fermi theorem. It depends on the time, because before, when we didn't have computers, it was more difficult to envisage, but there's always an ethical question hovering in the background. You have to think of the consequences, and it's very difficult to predict what is going to happen down the line. And it's been said about artificial intelligence several times. It's obvious that you're not going to use the power of mathematics to create artificial intelligence. You can have driverless cars, but they're not that many applications. So perhaps we need to do more maths. But as terms of ethical questions, it's difficult to predict the usefulness because we don't know how the artificial intelligence is going to behave. But you have to be careful, of course.
Anton, what do you think about that? Well, it's very difficult to predict the future. Nevertheless, whilst being careful, scientific research has to progress, because it can help us having a full control over the situation. One shouldn't try and hide, but simply go ahead with open eyes. Stanislav, you're saying that there aren't enough mathematics in artificial intelligence, but with the power of deep learning and networks, could you use artificial intelligence to progress in mathematics? Well, I even attended once a meeting of the International Medical Union. They organized a special symposium on this issue. And indeed, there are already systems which use mathematical demonstrations. The results are not ideal yet, but things are progressing. The question was raised whether we could use artificial intelligence to solve theorems or conjectures. Maybe in 2 or 3 years' time that might happen. But as far as AI is concerned, it's a question of phases. Are we going to progress one step after another? Is there going to be a limit? Is there going to be a kind of physical limitation which will prevent us to go any further? Maybe in 20 or 30 years' time things will have changed. But that's a very interesting question, because I mentioned Newton's theory to explain the movement of planets, and Fourier. We don't have a similar theory to explain what's going to happen with artificial intelligence. Allow me to enter into quite a different realm now. We have 5 evenings to discuss about mathematics, but during the rest of the year, I don't think that there are many mathematicians in the media. As a scientific journalist, I interviewed mathematicians 2 or 3 times over 20 years. And in 2014, I wrote a paper about Martin Herer's Fields Medal, and I discussed it with Martin Hallett, who is professor of mathematics in Neuchâtel, and he said mathematicians don't communicate enough. It is our fault. We should have more people like Cédric Villani. Is that true? Should it be mentioned more often in society in general, as we did this week? What do you think about that? Indeed, yes, possibly. But on the other hand, science in general is not enough mentioned in media. And it's particularly true for mathematics. And I quite agree with you. Do we need Cédric Villani for that? He's a very good friend. I'm not sure he's the only one to interview. And this medal, which you obtained in 2010, gives you an additional responsibility. The fact that other field medals laureates didn't do the same thing. Well, indeed, it does. Other people who received the Fields Medal said, it's not my job. I'm not going to do that. I'm not going to communicate with the media. Do you think you should? Yes, it's a kind of mission. Yes, indeed. I try to speak to the general public about mathematics. Maybe not the same way Cédric does, but I talk with school students. What should we do to have more mathematicians enter the field of mathematics? Well, I don't know exactly. Maybe the way mathematics are being taught at school should be changed. Something more interesting should be made in connection with other topics, for example, or by studying interesting problems. That might be the most interesting way of going about it. Elise, another question online? Someone asked us, what are the open problems in percolation? Well, in percolation, I showed several conjectures, but for percolation on hexagonal grids. For square grids, it can't be shown so far. But very recently, someone showed with two colleagues the half of what has to be done. So problems are still to be solved. Maybe in this is a terra incognita, an open field where we hope to see new phenomena, but we can't describe them in mathematical terms yet. No further questions online so far, so we're coming to the close of this evening. Let's take stock, Anton, with an observation I made. By preparing this evening, I read an article of the Boson Globe about this Conway knot problem dating back to 1960s, and a young mathematician who is called Liza Piccinino decided to answer the problem, and she solved it within 1 week. This shows, I think, the dynamism of that branch of mathematics. So people can decide that they want to solve a problem, and within 1 week they have done that. My question to you, Anton, what is the what kind of stock can you take of all these evenings we've spent together? Well, obviously it's very difficult to take stock after 5 very different presentations, which were all of them particularly excellent. We were very happy to meet with these 5 great mathematicians who all have a different career path, are interested in different topics, have a different temperament, and yet they are all people who contributed to improve mathematics. maybe that is an example of the fact that everybody finds their own way in mathematics. Mathematics is just as open and as wide as any other topic in life. So there is room for each temperament, each career, each path. Everyone can choose their own way towards success. There is not one single way to do so. So everybody who is interested, particularly young people who are interested, are very warmly invited to join us and do mathematics with us. Thank you, Anton. So we are coming to the close of this evening, and you know, Stanislav, that a question is still awaiting you, which I found in an old magazine dating back 1969. Are mathematics an invention of the mind or a discovery? Do you discover mathematics or do you construct them with your intelligence? Well, first of all, I'd like to add 2 words to what Anton just said. Mathematics is the most democratic science. If you want to progress in physics or chemistry, you need a lab which costs a lot of money. Well, in mathematics, you can work alone without any resource. But you never work alone. You always work with colleagues and friends to discuss interesting problems. The world of mathematics is one of the most democratic forms of science. Not only is it interesting, but you have also many interactions with other people, and there are many open questions. And to answer your other question, I'm a rather Platonician mathematician. I believe that if you think too hard about your question, it's impossible to do mathematics. It's just like the story of the insect with many feet who started thinking with which feet they should start moving around, and then they didn't move at all. Well, thank you. Thank you for this anecdote and for your contribution. Let me remind you that you can have a look at these evenings again and again on the internet. You will also find on our website an exhibition about mathematics very close to the topic that has been broached tonight. This exhibition is called Belle Math and is online. And then you can also find videos which were made by the team of the science team in Geneva, who decided to film their contributions and put them on the website of the colloque.ch. Well, time has come for me to thank everybody who's contributed in this colloquium, to start with the University of Geneva, the whole team, interpreters, Anton Alexeyev for organizing the scientific part of this colloquium, and of course the Wright Foundation for having made it possible. The president of this foundation is with us, and he'll have the last word. Thierry Courvoisier.
Thank you. We've spent a whole week trying to throw light on a number of aspects of mathematics. Not all of mathematics, but some aspects of mathematics. And I can imagine that for many of you out there, you will have noticed that everything you heard over the week has very little to do with what you heard when you were sitting in maths classes at school. And that's what's extraordinary about this week, is that we've been able to give a taste of mathematics and for mathematics to the world at large, and get people to understand that mathematics is a game, is an elegant game. There's a lot of brilliance in mathematics, and it's a pity, it's a great shame that we don't acquire this taste for mathematics at school. I'd like to point out that all the people who are going to see the light show that will be organised by the Wright Foundation, that will be shown on the walls of Université next year, that this show for all those who are interested in maths and others will understand the same message, that mathematics is something that's brilliant, aesthetic, beautiful, and it's not simply sums and divisions and multiplications, etc. So there are a number of people we need to thank warmly that were involved in the organisation of this week's conferences. As you can imagine, it was particularly complicated. I'd like to thank our speakers. I really like to thank our speakers. 5 brilliant presentations on 5 different aspects of mathematics, and I'm very grateful to these extraordinary people to have taken time off to be with us this week. I'd like to thank Anton for having worked with you to organize this colloquium, and obviously we can't listen to your rounds of applause, but I'm sure nevertheless that the colloquium was successful thanks to you. I'd also like to thank our colleagues who introduced our speakers and also presented the questions, relayed the questions, and who emceed these evenings. So I'd like to thank the whole School of Mathematics for having sent in people to do just that. Sarah, Simon-Dada, and Olivier, obviously you've made these evenings pleasant. Again, many thanks. Sophie Hulot and Fanensis Bane, I don't know how to put it really. I mean, you know, they've been working so hard for so long to see to it that we have a wonderful week, and they deserve a warm round of applause. Mrs. Lozano, Ascension Lozano, is the heart and soul of this foundation, so she also deserves our heartfelt thanks. So I imagine you've drunk up your beers or glasses of wine. I wish you a very pleasant evening, and I'm looking forward to meeting up with you next year round for the last light show, and in 2 years' time for another Right colloquium. Thank you very much.